to write it down again. And everybody's been waking each other up at 2 o'clock in the morning. Okay. So we ended last time going through one of the rare exercises in fluids where you can actually exactly solve a problem. And the problem that we solved was a problem of flow between two plates, two infinite long plates, with a pressure gradient in the x direction, which was oscillating with a frequency omega. Okay? And the solution that we found looked like this. We had u of omega and y given by I over rho omega dp by dx, which is just a uniform. This is just a number. Times 1 minus cosh of ky over and these boundaries were in the y direction at plus a over 2 and minus a over 2. Okay, and the full solution was u x is equal to u of y omega e to the I omega t. Okay, and of course k is equal to the square root of I omega over nu. Okay, and then we took this solution and we plugged it into Mathematica and we plotted it. Okay? And what we saw was that well, to plot something you have to put some parameters in. And the parameter we chose some values for the various parameters that we have. One parameter is sort of relatively uninteresting, which is the density and the magnitude of the pressure gradient. This we just adjust so that we can see some motion. Okay, but then there was an interesting combination of parameters over here in the Ka kind of term, which gave us a combination that looked like a squared and omega and a nu. Okay. And so then we fixed a, that's just geometry, we fixed that to 1, and we noticed that we could just tune omega relative to nu, so we fixed omega, and we tuned the viscosity. And what we saw was that by tuning that parameter, we could get flows that look like this. So this is for a large value of nu, of order 1. Okay, so here we have our nu, I put it into 1, and this is the flow that we get. This is plus a over 2. This is minus a over 2. Okay, so this is the y direction. You'd have to rotate it 90 degrees to match the picture. And then we started reducing the value of nu. We saw that as we reduced the value of nu, in this case it is 100 times smaller, we started to see a change in character of the flow. And if we went even a little bit further, this is now value of nu, which is 10 to the minus 4 times the one that we had originally, then we saw that the flow really changed character, had no spatial variation except at the very edges, and just sort of looks like a flow that's going back and forth, like a plug. Okay. And so what I want to do today is start by starting to develop some intuition about what's going on, about why the flow changed its character by being adjusted by this parameter. Okay? So does anybody kind of have a sort of idea of what happened here as we change this parameter? Physically in the flow? The relationship between inertia and friction. Okay.
This is all about inertia.
Okay, so this flow over here looks like you're just taking a block of fluid, right? And it's a solid block, and you're pushing it back and forth, and it's oscillating back and forth. So that looks like something which is dominated by inertia. Okay? Whereas if we look at the other flow up here, okay, it looks nothing like that. It looks like you're pushing the flow, right? And then there's a lot of friction at the edges, which is why the speed is always 0 at the edges. And this looks like a flow that's dominated by viscosity. Okay? And in general, in fact, you can't solve a problem for arbitrary kind of relationship between inertia and viscosity. So what I thought I'd do is we'll kind of look at this solution, see that we noticed that it has these two regimes, and we're going to go and sort of try to understand at the level of the equations where these two regimes from. What we're going to do is we're going to do some scaling. We're going to estimate the importance of the various terms inside our equation and try to then see if we could have solved for either one of these flows without solving the full system. Okay. So this is a sort of very general thing that you can do. It's not peculiar to fluids, although many people encounter it in the course of fluid dynamics the first time. So let's think about our equation. So our equation was, everybody remembers the equation? Help. I have rho dt of v plus u dot grad u, okay, is minus yes, that's my point. Okay. You might as well get used to it day one. Okay, so what do we have in this? So what we want to do is we want to kind of imagine that our solution, we could either have an experiment and see our solution, or we could imagine our solution is going to have some sort of characteristic speed, right? It's going to involve some characteristic speed. It's going to involve some characteristic size. We know this from the way that we set it up. So what we're going to try to do is we're going to try to, in advance, put in these characteristics of the solution that we expect into the equation and look at the weighting of the various terms inside the equation. So our parameters in this equation are the speed of the flow. And the units of the speed are length over time. Okay. Then we have, what do we have? We have x. We have gradients in x. Right? So we have a spatial variable. And this has units of length. Okay. Then we have a time derivative. So this has units of time. And then finally we have a pressure. And pressure has units of mass over length times squared. Okay. So what we're going to do is we're going to kind of try to rewrite our equation in terms of dimensionless variables. So we're going to rescale them by the characteristic sizes. So we're going to assume that our solution has some characteristic velocity, right, which has the same units as length over time. Okay. We're going to assume that it has some characteristic length, which has units of length, of course. And now we have to kind of pick a characteristic time. Okay. And here there's kind of different things that you could imagine doing. Right? In general, if you have a problem that doesn't have a time scale in when you're setting up the problem, for example, you're just sort of pushing fluid down a pipe and you're not oscillating anything, then all we really have available to us are these two other scales here in the problem. Right? So we could form the combination L naught over U naught, and this would have units of time. In our particular case, we also have a frequency. So we could also have chosen something like a frequency to rescale the variables. And finally, we need something in order to rescale the pressure. Okay? And here, interestingly, we have two choices. Okay? Can anybody help me find the two choices? What combination of things that we have in this equation could have the units that pressure has? Density. We need the density because we need the mass part. Huh? Velocity, U naught squared. Very good. So this has units of mass, right? Then there's a 1 over L cubed for the rho, and then there's an L squared. So that gives us a 1 over L, and then there's a T squared, so that's good. Is there another choice? Viscosity, okay. What are units of viscosity? Pressure second. This is kinematic viscosity. Okay, so it's length squared over time. Okay. Remember when we wrote down the diffusion equation for momentum, we had this combination coming in. Okay, so we have nu. Okay, so that's good. What else do we need to make this work? We're going to need a mass density because we need the kilograms or the mass units. Okay. Okay, then the rest is kind of, you just fill the gap in with u naught over L naught. Okay. And so the idea is that what we're going to do now is we're going to take these combinations of parameters that give us the units of the variables inside our problem, and we're just going to rescale the variables inside the problem. So for each variable, we're going to have a, can people see in the shadow? No, not really. Man, the real estate here. Okay, so, okay. We're going to have a u is going to be equal to our rescaling times u twiddle. Okay, and the same thing for all other variables. So p is going to be equal to p naught times p twiddle and so on and so forth. So let's put that into our equation. So we have a rho, okay, and then we're going to have over here, we're going to have a 1 over our t rescaling variable. So let's choose L naught over u naught. Okay, so we're going to have u naught over L naught d by dt twiddle, okay, of the velocity. So this is going to be a u twiddle, and we pick up a u squared over here. Okay. Then if we look at the second term, we're going to have again, we're going to have two. We have a u twiddle dot grad twiddle of u twiddle. Okay. And so we have a u naught, and a 1 over L naught. So that comes out with the same factor over here. Okay. And then over here we have a minus, and then we have a 1 over L naught. That's the rescaling of the derivative, and then we can choose one of these two. Okay. In fact, we'll sort of maybe try to choose them both. So we're going to choose a factor of rho u naught squared, or rho nu u naught over L naught as our two choices for p twiddle. And then finally we have nu, we have rho, and then we have a 1 over L naught squared for our Laplacian squared, and then we have a u naught. Okay? So now all we really have left to do is to kind of simplify our expression a little bit. And so we can do that as follows. We can just divide everything by this. So we're going to have dt twiddle plus u twiddle dot grad acting on u twiddle. Okay, and this is going to be equal to, we're going to have a minus, okay, we're going to have grad twiddle. Then depending on our two choices, we're going to divide. So we're going to have the rho goes away. We have on the bottom a u naught. The L naught goes away, and we divide it by this. So we have a nu. Am I missing an L naught somewhere? Oh yes, there's an L naught from here. So we have an L naught over here. And then on the bottom, we're just going to have an exact cancellation. So we have 1. This is p twiddle. And then over here, we're going to have the rows are going to cancel, so we're going to end up with nu over u naught L naught times del twiddle squared u twiddle. Okay. What has happened? What do we learn from doing this? Say? Yes, so first of all, we've learned, basically, that's a very good remark. We've learned that basically this equation over here, I mean the Navier-Stokes equation in this particular case, is really only differs from one situation to another by one parameter. And that parameter is a combination of the viscosity, the kinematic viscosity, the velocity, and the density. So in other words, the density doesn't really matter. Sorry, the velocity and the length scale of the problem. The density doesn't really matter. So all the equations, all the problems that we can go and solve, right? Really only, the character, that type differs by one parameter, okay? At least at the level of the equations that you write down. The boundary conditions in the particular situations can be all over the place. And also, can you sort of guess? So we have a parameter over here. Everybody, I'm guessing, will know what it's called. Okay, it's called the Reynolds number, okay? And it's equal to u naught L naught over nu. Okay, and can you sort of see? So it appears, right, in this equation as a ratio between this term over here, okay, which was our term which described the effects of microscopic diffusion, viscous diffusion of momentum, and this term over here, which was our inertial term. Okay. So in fact, it's a parameter who, depending on its importance, right, depending on whether it's large or small, is going to give importance to this term over here relative to this term over here. Okay. Now the pressure in this problem over here is what's driving everything. So the pressure always needs to be important, whether or not you're talking about this problem or this problem. And the two choices we had for rescaling it, which we're going to make, depend on which of the two kind of parts of the flow we want to consider as important. Okay. So is everybody happy with this basic idea? Yes?
So I'm not clear about the pressure, the coefficient in front of the pressure.
Okay.
Because since there are two choices, you can have either 1 over RE or 1 in front of the pressure.
Yes. Well, so the question is, in this particular case, for example, the pressure is driving the flow, right? So it has to be relevant. I can't not have it in my equations. So if I'm considering viscous flow, I'm going to choose this scaling over here. And if I'm choosing inertial flow, I'm going to be choosing the scaling over here. Right? Now, in practice, you can actually choose either, right? Since the pressure in these incompressible problems just appears as a sort of Lagrange multiplier that goes and adapts to suit the rest of it. The important thing is the balance between this term and this term over here. But I find that this kind of aspect is usually ignored, so I thought I'd put it in over here. Okay, so what we've done is is an example of something that you may or may not have done with all the equations that you learned in physics. You can take the equations, you can put characteristic scales that you have inside your problem inside the equations, and then you can learn about the importance of the various terms, and what they're driving in the problems. Now, of course, many equations in physics are linear. Many of the ones that you study are first. So very often, these combinations of parameters don't really affect the character of the solution, but just the kind of overall sizes of the effects and the relative effects that you study. But here, they're really important. Yeah.
Could there not be a third scaling for pressure where you've got rho nu squared over L naught squared?
Rho nu squared.
Always be squared.
Did I miss one? There's a third one. I'm assuming you did the dimensional analysis, right?
Yeah.
Yes. Rho nu squared. Yes, I guess you could have something like that, and I haven't thought about the consequences. Rho nu squared over L naught squared? Well, it depends on the value of nu. Yeah. So. Yeah. Good question. Okay. Usually you only get this one. So now you got 2 and 3. So it's an exercise to think about it. Okay, so so what we can do now is we can say, okay, suppose that we couldn't just find that exact solution, right? But suppose that we know that our problem, because we've looked at it, or we know in advance, is going to be dominated by this kind of inertial slug-like thing. We're pushing this thing really, really hard, so we expect it to react almost like a solid. Okay? That's equivalent to saying we're going to take the limit for the Reynolds number going to infinity. Okay? So we're going to consider a case in which the velocity and the length scales are very large. This product is very large compared to the kinematic viscosity. Okay? And so what we can do if we do that is we can ignore this term over here. Right? And the equation that we're left with, I'll go do that over here. The equation that we're left with for the Reynolds number going to infinity is dt plus u dot grad u is equal to minus the gradient in the pressure. Okay, so we've dropped our viscosity out of the problem completely. Now remember, for our particular problem, which is sort of one-dimensional, by the same reasoning, we can ignore this term over here. So the equation that we have is dt, I guess I should put twiddles over here, of u, twiddle, is equal to minus grad twiddle of pressure twiddle. Yep? We dropped this term because of the one-dimensionality of the flow. So the u dot grad is a d by dx. It's a d by dx along the flow lines, and there was no gradient in the velocity along the flow lines. Okay. So if we think about now what we would have done if we were just solving for a solid mass moving back and forth, well then we would have done F equals ma. So what's our F? There's a pressure. Good. What do I need to make this into an F? I have to multiply it times the area of the channel. Okay. But this is not the pressure. This is the pressure gradient. So the pressure difference, I also have to multiply times the length of the channel. Okay. And then on the right-hand side, I have the mass. Well, the mass is the density times the area times the length, exactly, times the derivative of the velocity. And so if I subtract these terms over here and I rescale my variables, so this becomes 1 over L naught, the p twiddle as a rho u naught squared. Did I get that right? Yep. Yes. There's a minus sign. And then here I have a rho. And then I have a 1 over the time rescaling. So I have a u naught over L naught for the 1 over the time derivative times another u naught dt twiddle u twiddle. Okay? So I can cancel these two, and I have exactly the same equations. Yeah?
Maybe you're going to get to this, but in the limit of very large but finite Reynolds number, you have a singular perturbation. And
We're going to get to this.
Okay, then I'll
Absolutely, one step at a time.
All right.
Okay. Everybody happy? Okay. So what we did is we basically just said in advance, we anticipate that inertial effects are going to dominate our solution. And the equation, and so we took our equation of motion and we dropped a term because we thought it wasn't going to be important. And then we saw that we just got, two things. One was, first of all, an equation that does indeed represent just the motion of a mass that goes back and forth. And the other one is that quantitatively, the answer agrees, right, with the limit in which the viscosity is very, very small. You saw that this thing was just oscillating back and forth like a plug. So we've recovered one limit, at least most of the solution in one particular limit. Now, the other thing that we could have done is to take the opposite limit, which is to say the Reynolds number goes to 0. And in that case, for our problem, this was going to become, let's see, rho nu d2 ux by dy squared is equal to gradient of the pressure. Okay, and so this you'll recognize as just a diffusion equation, okay, which is driven by the pressure. It's a linear equation, and so we can just solve it. Okay. Okay. So we can find solutions. So does anybody know how to solve this equation in general? This is just a constant driving term. Okay. So our solution is at most quadratic. So we have a DC term, we have a linear term, and a quadratic term, and then we're driving it. Okay. So the solution in general is going to be rho nu ux is equal to minus grad p times a squared a over 2 squared minus y squared. Okay. And the reason why these constants in general, ux, right, can just go with some number plus some number which is linear in y plus some other number which goes with y squared. Okay, and the way in which we fix the constants is that the values here and here at plus a over 2 and minus a over 2 have got to go to 0. This is our boundary condition that we mentioned last time. Okay? And in fact, what we can then do is we can go and, well, first of all, this if we look at this function over here, this function looks like, if we plotted it this way, right, with y this way like I did before, and we plotted the velocity, it looks like it has a quadratic profile, which is exactly what we had from our exact solution in this limit over here. And in fact, you can also verify that if you take the limit of your solution, I over rho omega, actually, since I've written it down before, I'm not going to repeat it, u of y omega, we take the limit, we expand it in powers of omega, we're going to recover dx of p over 2 rho nu times a over 2 squared minus y squared. Okay, yeah, you can do this as an exercise. So you can see that indeed, right, by dropping the terms in your equation in advance of solving the problem, and then solving the problem, we were able to recover one limit of the general solution. And by neglecting the other term, we were able to recover the other limit of the solution. Okay? Guys, do you mind just doing this later? It's incredibly distracting. Okay, so what did I want to say? Okay, so, in this particular case, this was an exercise. We didn't really need to do this because we were able to solve the problem. Okay? But in general, this is not possible, and so doing this in advance makes the difference between you being able to solve the problem or not solve the problem. Okay? So what I'd like to do is consider make a few remarks about these two limits independently, and then we're going to go and worry about the crucial question, which was raised by Alex, but also which is kind of the obvious elephant in the room, which is, what about those little wiggles at the edges of our inertial flow? Like, do we really capture the whole solution? Is it as easy as this? You just make an approximation, then you can solve the problem, and now you can do magic like you couldn't do before, or is there something more we need to worry about? And so the first kind of limit that I want to consider is precisely this limit that we considered over here, right? And I want to just think a little bit about the character of this particular kind of equation of motion that our equations of motion for fluids became. Right? They became this very simple equation over here. Okay. So can anybody sort of point out some features about this equation? Doesn't depend on time explicitly. Very good. So what does that suggest? It's instantaneous response, okay. And what does that suggest? So you have a solution, you have an equation. In fact, it's a linear equation, so it has unique solutions. And the response is instantaneous. Reversibility. So if you do something and then you undo it, this equation says that everything should just go back to where it was. Okay. Reasonable, right? I mean, that's what the math is saying. When you think about a fluid, does that seem natural? You need to do it very slowly, right? And what they say you have to do it very slowly is the Reynolds number. But what this equation is telling us, right, that in this particular limit, we don't need to worry about the time in the problem. The fluid isn't going to develop a life of its own. It's just going to respond to things. And the first time I saw this, I kind of thought, well, that's really funny. I've never seen a fluid go back and do do what it was supposed to do. And then I was shown this remarkable video, which I believe how many people have seen the Taylor video? Okay. How many of you have seen a live demonstration of the Taylor experiment? Okay, good. I thought I'd show the video, and then I thought, no, with YouTube everybody's seen it. But anyway, so if you've seen it before, you know what's coming, but you've never seen it, so come closer so you can see it live. If you've never seen this before, then be prepared. Now we haven't practiced this, so be warned. Okay. What we have over here, let me just say a few words.
Wow.
Okay, so what we have over here is a very viscous fluid, right? It's corn syrup. Okay, I actually didn't look up the viscosity of corn syrup, but you can. Somebody can on Google right now, and they can estimate the Reynolds number for what we're about to do. So we have corn syrup, and it's in between two cylinders, and I can rotate the cylinders relative to each other. Okay, so I can by taking this lever over here, I can rotate the inner cylinder. Okay, and that's going to rotate the inner cylinder relative to the outer cylinder. Now, of course, when you look at this, you don't see the two cylinders, right? And that's because there's this wonderful coincidence where acrylic is index matched by corn syrup. Anyway, so this is corn syrup with stuff in it. So you see, I usually live at high Reynolds numbers. So for me, it's just like, it's a diffusion constant, millimeters squared per second in water. Okay. Now the danger, of course, what we want to do, right? Everything which we said about reversibility depended on the fact that we were going to do something and undo something. Okay. So what could go wrong? You could have air, for example. Exactly. So be prepared for something to go wrong, which involves air. Okay. Let's try to get the air out. This is I'm gonna try this other approach over here. Let's try this approach over here. Okay. So this is like those scary films. Okay. And we need to rotate this a little bit. Okay. And I'm gonna go in. Whoops. And I'm gonna put a blob. Woo! Okay, what's going to happen now? Tragedy has struck. Okay, no, we can fix this. The air has surfaced already. Okay.
Same thing backwards is reversible.
Thank you. Okay, I don't see much air over there. I'm hopeful, right? Yeah. Okay, let's just do it. Okay, so we need a volunteer who kind of just enforces, helps me do the reversibility thing. So press down there. Okay, good. Okay, so can I count? Yes, I'm counting from here. Everybody count. What's happening? No, come on. You know better than that. What's happening? Shearing. So there's a velocity gradient, right? So the parts at the front of the blob are getting out of sync with the parts at the back of the blob. Okay? So it's getting nicely smeared out. One revolution. This takes patience and strength. 1.5 revolution. Woo. Reversibility. And 2 revolutions. Can anybody see the droplet? Ready?
Keep rotating into the end of it.
We can keep turning till we could, but then we wouldn't get the boundary layers. Don't you want to know about boundary layers? Okay, I made that 3. Almost. 3. So what's happened? It's been sheared, right?
Yeah.
But the equation says that if I do this backwards, we're just going to find out what happens to people who believes in equations. Huh?
I lack faith here.
You lack faith. Good. I always lack faith. One.
Oh.
I went 3. 2.
Do you believe? This is witchcraft.
Are we going to have one of those religious moments where you're like, I believe? And
Yeah.
3.
So now is the moment you take a bow. And
Crazy, huh? There you go. Okay, so by now somebody's looked up on Google the viscosity and can tell me the Reynolds number.
Okay. So what does centipoise mean?
Oh no, we're not going to do that. We're not going to convert between units. Huh? Somebody do this in the meantime. The point is it's very riskless and the Reynolds number is very low. Just to kind of stimulate some kind of initiative, some further initiative in looking things up and making your own estimates. Does anybody know what the value of the kinematic viscosity for water is? No? Okay. The kinematic viscosity as units, it's a diffusion constant. Okay? And it's really nice in water because it's 1 millimeter squared per second. Okay? It's a useful number to remember. Anybody know the kinematic viscosity of air? This one you can actually estimate from first principles. 10 to the minus 4? I'm getting varied answers, but they're all 10 to the minus a lot.
It's almost the same.
It's 15 millimeters squared per second. Okay? I'm sensing some surprise at this. I'm saying that the kinematic viscosity, which is the relevant one for the Reynolds number. Okay, so remember what happened, right? We wrote down our equation, we de-dimensionalized it. And where did the density go? The density was gone, right? So the density has been absorbed in the coefficient for the diffusion, right? Which means that the relevant nu for the Reynolds number, where you do u naught L over nu, is the diffusion constant of, well, we'll see what it's the diffusion constant of in a moment. But so if you want the actual viscosity, intended as the force that you feel as you shear something, you have to multiply these by the density. And so there you'll see that the one for air comes a lot less. So anybody knows what the Reynolds number for an airplane that took you here is? Sorry? 2,000. That was one guess. Okay. 20,000. Any more guesses? 100. Wow. This is awesome. Okay, why don't we just kind of like figure it out, okay? So what's the Reynolds number? I have a hint. It was written on the board before. Okay, it's u naught L naught over nu. Okay, so in air, this is 15, right? Millimeters squared per second. So if we're going to do it in meters squared per second, it would be 15 times 10 to the minus 6 meters squared per second. We're going to do SI units. Anybody can tell me what L naught is for an airplane wing? 50 meters? 100 meters. Okay. That's a heck of an airplane. Okay. Any more offers? 1 meter. That's actually closer to the answer. Which length should you choose in the problem? Like an airplane wing is wide, but it's also got this length, right?
Oh, okay.
The thickness, that's another possibility. Yes, exactly. It's more like something which is a smaller dimension than one of the bigger dimensions. Okay? So I'm going to take that to be 5 meters. This is like the A380. There you go. Okay. And how about a speed? 1,000 kilometers per hour. Wow. Okay. Can anybody tell me what the speed of sound is in air? So it's less than that. Okay, so let's take 200, something like that. Okay, I'm going to take 200 meters per second. Okay. So what do we get? Okay, so we get 2/3, right, times 10 to the 8. So it's very, very high Reynolds number flow. So 10 to the 8, yes. It's a sort of, an 8. Okay, anybody here work with colloids? Interesting. Okay, liquid crystals. A little more. Okay. What's the typical Reynolds number for a colloid or a liquid crystal? 10 to the power of -6. There you go. So you can do this at home. You can assume some sort of very high speed for a colloid, 1 micron per second. You can put in a dimension of a colloid of 1 micron and use the viscosity of water, and you'll find a number that's around 10 to the -6. It's a fun exercise to actually estimate some of the Reynolds numbers for various phenomena, especially when you get to flies. So you guys can do that, and we'll talk about it next time. Okay. And incidentally, we took in this particular case a very special version of the Navier-Stokes equations. We made these approximations, right? The approximation we made, though, it was incompressible, and we said that there was no thermal conduction, and I think that's mostly what we made. Oh yeah, and we said there was no kind of expansion type viscosity. If you don't make those approximations, you then have to go through the same exercise that we did over here, and you have to put all the relevant scales for your problem in. And so what you'll find is that in general, it isn't just one parameter that governs the entire set of the equations, right? But there are many parameters. And so there's a kind of, you can look up dimensionless parameters in fluid dynamics on Wikipedia, and you'll find many, many parameters. And one which sort of just came up just now, spontaneously, was if you're considering the fluid to be incompressible, the validity of this approximation depends on the ratio of the characteristic speed gradients in your problem and the speed of sound. Because once you reach speeds gradients that are comparable to the speed of sound, you're going to compress the fluid, and that approximation is no good. So there are many, many numbers, and you want to at least know the numbers that are relevant to you. Yes?
So typically when you see in the flight monitors, like the typical airplane speed is 1,000 km per hour. And
500 miles an hour.
Per hour. Yeah. And
Factor 2 is important.
Yeah.
They start to fall apart at around
and
600.
Typically the speed of sound is 1,200 km per hour. So, I mean, they are pretty much comparable, right? So in such circumstances, can we use the incompressible approximation?
That's a very good question. So you can use the question is basically airplanes go pretty fast, even when you compare it to 300 meters per second. Okay? Not faster than it, but they're not like a factor of 10 to the -3 smaller than that. They're like a factor, 1.5 or something less than the speed of sound. Can you still use the approximation? 0.8 Mach, for example. And the answer is that I don't know the precise number, but it turns out to be a very good approximation to consider air as incompressible up until you're approaching, I think, around 0.8, 0.9, something like that. So they do have to take a little bit compressibility into account, but by staying at those speeds, they're staying below the threshold at which all the interesting phenomena that happen when you allow something to be compressible, like shocks and all these sort of things, don't start happening. And if you push the airplane a little faster than that, it'll start shaking like crazy, and wings will start coming off, and all that sort of good stuff. This was one of the problems at the beginning, right? They dive to get the speed, and the thing would fall apart because of instabilities, which we won't get to. Okay, but we'll get to a close kind of cousin of instabilities, or at least something that is a precursor to many instabilities in fluids, by going back to our exact solution and looking at the plot of our exact solution. What's going on here? Oh, here I was trying to find the stability of airplanes, but that's a whole separate situation. Wow. I was busy last night. Okay, here we go. Yes?
In your experience as a pilot, have you experienced the stability of
No. Does that answer the question? Okay. So And as you can never mind. So let's look at this, right? So we looked at this before, and we were kind of, digesting lunch, and what's this guy going on about? And, we have this big slug that goes back and forth. If you look at it coarsely, it looks exactly like that. It looks like there's a big slug of fluid that's going back and forth uniformly, right? But if we look at it a little bit more carefully, right, then we notice that there's something going on at the edges over here. It's not exactly a inviscid fluid. It's not a fluid where we don't have to care about viscous effects or friction or anything like that. We need to, there's a little signature over here that says something's going on, and it's going on close to the edges. So we need to worry about this. Can anybody help me estimate what the width of this is? Look at the Reynolds number. Okay. That's not a length. Pick a length that makes it 1. There you go. Okay. That's a very good way to proceed. But there's another one. What were the parameters that we put inside our problem?
Frequency.
So in our equation, right, we had a viscosity, okay, and density and other stuff too, right? And then in our boundary conditions, what did we have? We had a zero velocity, but we also had, we're looking to make a length. And the viscosity has units of length squared per unit time. So what do we need to make a length? A frequency. Exactly. Okay. So in fact, if we go back, we think about expanding our solution. Where do we expand our solution? We expand it over there. Okay. When we looked at expanding our solution, the parameter that was relevant for us, right, was a parameter that was this k over here, which was the k that appeared in the cosh, and this was proportional to. So first of all, this has units of 1 over length, right? And this was proportional to omega over nu. Okay? This is a long way around to say that if we have our omega inside our problem, okay, and we have our viscosity inside the problem, then we can make a length scale, okay, out of these two. And the way in which we do that is by taking nu over omega and taking the square root of this. And so if we think about this limit of the problem, it's a limit in which either the frequency is really high or the viscosity is really small. Right? So this is sort of tending to the limit in which we're at high Reynolds number. And what we find is that in fact, right, there can exist in our problem a length scale which is smaller than the separation between the two plates. And this length scale is formed dynamically by the solution of the equations itself, and it comes from this oscillation. And if we estimate this length scale, you'll see that from the expansion, it is in fact corresponds exactly to this width over here. So I think this is probably a good time to take a few minutes break. So we'll come back in about 5 minutes, and we'll talk about how to treat what's going on in this very small region. Thank you. Yeah.
Exactly at what point do I start worrying about the compressibility of the air?
You have to ask the engineers to get the exact number, but
Yeah.
I mean, I know that airlines go up to like 8, I think.
Yeah, that's what I thought.
8 or
They
9.
fly at like Mach 0.8 or something.
Yeah,
So 0.8. Zero. What did you say?
0.8, something like that.
Yeah. And I thought, but doesn't that also mean that there's some airflow over the wing that's actually going faster than the airplane is going?
Yes, there is,
Right.
absolutely.
So that means that air has got to be pretty close to the speed of sound.
Yes.
And does that change the lift characteristic of it, or?
Yes, it's going to come in.
So you can't do the sort of that complex integral thing, or calculate the vorticity around the wing?
Well, no, but it's not far from that answer. Like these things don't change dramatically as you include these effects.
Because something dramatic happens when you approach the speed of sound.
Yes, but
But
that's
that's nothing to do with air going supersonic over the wing.
I think that's turning on shocks at the leading edge.
Oh, and then you interfere with your own shock
Yeah.
cone. Oh, so like the wing pokes into the shock cone of the nose of the plane?
Yes,
I think you can see that in the fighter when the fighter goes over.
and there's a shock generated from the wing that hits the rest of the thing. And
Oh yeah, I've seen those pictures because there's a
yeah,
there's that.
you get the sonic boom coming back off the end of the airplane.
Yeah.
So, so you have to have different design for supersonic speed compared to like subsonic speed.
Oh yeah,
So that's why like the fighter jet has kind of a triangular shape rather than this kind of.
yes, all that stuff comes into it a lot.
So apparently A380.
The other one is you want it to be very unstable.
Okay. And A380 is 80 meter.
Is what?
A380, the length of A380 is 80 meter.
Oh, okay, but that's the length of the airplane.
The length
But the length of the wing is about 5, right?
Yeah.
So,
Yeah.
when you said there are these two-dimensionless ways to non-dimensionalize the pressure,
Yes.
you really cheated, right? Because you divided by the Reynolds number in one of them, which you could do for anything.
Yeah.
So, I mean, so it's not really.
Well, no, because the I mean, so you have the viscous term
Yeah.
and the inertial term. Their ratio is always
Always
right,
given by the
but
Reynolds number.
the pressure adjusts itself in order to satisfy your boundary conditions and stuff. If a fluid's incompressible, it's just a Lagrange multiplier. And if you want to estimate the scale of the pressure correctly, it's going to be very different if it's an inertial effect or if it's a viscous effect.
Okay.
And the ratio between the two is the Reynolds
I
number.
see that. Okay, but I mean, there's nothing in the problem which gives you two ways to non-dimensionalize the pressure as opposed to anything else. Because
Right.
anything you could non-dimensionalize by multiplying it by arbitrary.
Absolutely.
Yeah.
But if you did the naive thing of just saying I'm going to take Reynolds to infinity, and you don't have Reynolds in front of the pressure, you throw away the pressure too.
I see. Okay. Yeah.
So that's
So
why.
That's why. Yeah.
Yeah, exactly. It's just that, usually people never discuss this. They just talk about those two terms,
Right.
and I'm like, well, I take Reynolds number to
Same.
infinity. I lose the pressure. What's going on?
Yeah.
We got a really silly question,
Yeah.
about which we're not really sure. So everybody always says that pressure is a Lagrange multiplier inside of the
Yes.
Navier-Stokes equation, but nobody ever shows why exactly.
Oh,
so
yeah,
the thing is always a little bit dodgy. I've got one argument, but I'm not 100% sure about it.
Okay.
What would you say about it? Like, what
I'd
would
say
be your
about it that
argument?
it's on my to-do list to do that calculation. I've spoken to people,
Okay.
and the way that I think is the simplest way to get to it is to start with a compressible flow.
With a compressible flow.
Yes, and then take the limit,
Okay.
and then see that the pressure is adjusting.
Because the way I've been
to the
shown it,
sort of
it's like just take the divergence of the momentum equation,
Yeah.
and you have basically a Laplacian equation for the pressure. That you can solve exactly because it's a Laplacian equation.
Yes.
Now, at the moment, you basically reduce the three equation of Navier-Stokes to just one.
Yes.
Because once you write the pressure like this automatically is enforcing the
Yes.
compressibility
Like a constraint.
condition. So it's basically like an effective constraint. And
Yes.
that's the way I think about it. But I don't know if there is any other way to think
Okay.
about it.
That could be a good way to think about it. I'd be curious to see it afterwards.
Well,
but yeah,
just,
you
just
can-
one just needs to take the divergence of the momentum equation.
Oh, okay, yes.
So
yes,
basically,
yes, yes,
the only term, the temporal derivative disappears. There's only the nonlinear term.
yes.
This disappears because there's again the
Yes, yes,
incompressibility.
yeah,
You end
yeah.
up with this.
And then you go, yeah, yeah,
An
yeah.
equation, and then you write the pressure. Basically, you don't have the pressure anymore in the equations.
Yes.
And this form here is automatically implying, is ensuring that the flow is incompressible.
Yes, yes. That sounds reasonable. Do I detect an accent?
Excuse me.
Do I detect an accent?
You do.
From where?
Italy.
È italiano, sì,
Yeah.
pensavo, infatti. Ok.
It is. To actually lick physics experiment.
We poured it in a few days ago, so
Yeah,
it should be okay. It's not like it's been there for years.
like the pitch experiment.
This is amazing, huh?
I'm just impressed you got an experiment, a demonstration to work.
Yeah, it's not often the
So
case,
what if
right?
you, like drive it really fast, like oscillatory drive?
Well, you can estimate the Reynolds number for me, right? I just did it about 6 times the speed. Go for it. 1, 2, 3, 4. Okay, stop. Otherwise, we won't be able to count going back. Oop.
Like the speed
It's cool, huh?
is cool, yeah. Just do the fast work. Yeah, because I
That's because somebody was going to estimate the Reynolds number, and then I was going to say, oh, so we could go faster, but nobody did it. It's 2,000 times. That's the ratio that you want, exactly. Okay. Okay, let's get started again. Did everybody see that, by the way? You can do this demonstration and go much faster, right? And if you estimate the Reynolds number, you can tell me how much faster you can do it and it still works. Exercise. Okay, so what I want to do now is say a little bit about how we capture this little wiggle over here, right? And what we sort of did immediately was some dimensional analysis, right? Given the dimensions in our problem, the driving of the problem and the viscosity, et cetera, and we were kind of able to estimate correctly the size of this phenomenon over here. But what I wanted to say a little bit more about is what's going on, sort of conceptually, right? Because we took our equation, we estimated that a parameter wasn't important, and so we dropped some terms, and then we proceeded, and we mostly got it right. Okay? But in doing that, we sort of neglected a subtlety of the process of dropping terms inside an equation. Okay? And this subtlety is sort of very important. It was something that puzzled people for a long, long time, and was solved largely by Prandtl with a set of sort of just brilliant experimental observations and intuitions. And it became an entire subject. And the subject is boundary layer theory. Okay? And as the name suggests, right, it's the theory of these kind of little boundaries between characters of flows which can occur when you make this sort of approximation. And it's a very difficult problem to kind of tackle in general. We could go through making the approximations that Prandtl made and derive an equation which is supposed to model a little bit what's going on in this boundary layer phenomenologically, and it would take us a lot of time. And also, it's very hard to sort of come up with analytical solutions when you do that. So what I thought I would do is consider a different problem. So we're going to consider a toy model. We're just going to consider a partial differential equation, okay? And we're going to do all the basic ingredients of what we did, right, when we made these two approximations, and we're going to see what happens. The difference is going to be that our partial differential equation is going to be exactly soluble. In fact, it's an ordinary differential equation. Never mind. Okay? So what I want to consider is the following differential equation. We're going to consider differential equation that's epsilon d2u by dy squared plus du by dy is equal to 1. Innocent differential equation. We're going to impose the following boundary conditions. U of 0 is equal to 0. Okay? And u of 1 is equal to 2. Okay? So can anybody tell me a solution to this equation? Bessel functions, okay. So as usual, I'm going to start with the solution and convince you it's the solution. I claim this is the solution. It's an exactly solvable differential equation. Does anybody believe this solution? Well, I don't, so I'm just going to check. Okay. So what's u of 0? U of 0 is 0, right? Here we have e to the minus 0. Which is 1, which gives me 1, right? So the top is 1 minus 1, so that's 0. Never mind the bottom bit. And this is 0, okay? So there we go, 0. Good. How about 1? Okay. Now we have e to the minus 1 over epsilon, e to the minus 1 over epsilon. These two are the same, so this whole thing is 1 plus 1 is equal to 2. Okay. So it satisfies our boundary conditions. There's a reason to do this. Okay. So it satisfies our boundary conditions. That's good. Okay, and I will leave it as an exercise for you to show that it also satisfies the differential equation. Okay, it's a relatively straightforward exercise. It's an ODE. But what I want to do is plot it. In the days before Mathematica, we used to do this. Okay, so I'm going to put u on this axis over here, and I'm going to put y on this axis over here. As y goes to 0, u goes to 0, so it's over here. Okay, and then we know that u is equal to 1, 2, at y equals to 1. It passes through these 2 points over here. Okay. Anybody help me plot the solution? Oh, that's just for fun. So we've enforced the boundary conditions, right? So we have this point and this point. Okay. Hint. Okay. Well, let's check what happens when y is less than 1. Okay. So what happens when y is less than actually no, sorry. Let's check what happens when y is much less than epsilon. Okay. So when y is much less than epsilon, epsilon is a small parameter, right? So the first term is going to go away. Okay. And then that top over there, if y is much less than epsilon, is going to go away. Okay. It's going to be very small. Okay. It's basically going to be 0. Okay. And it's going to stay very 0 until y becomes comparable with epsilon. Okay. And when y becomes comparable with epsilon, then this is still going to be small, right? But this term is going to become 1. Okay? So we're going to stay very, very small until we get to 1.
Should the axis be the way around? U should be on the...
U stays very small.
No, should U be on the vertical axis and Y be on the top?
No, I'm plotting it this way around.
Use the function of Y, right?
Oh, did I plot this the wrong way around? Am I mixing something up here? Yes, I think I'm making a mistake over here. What is the mistake that I'm making? So I'm going to consider small y. Okay. For small y, yes, u is equal to a small slope of y, and I've drawn a big slope of y. I think it's just the labels on the axis. Okay. Okay, good. Fun is over. Okay, and then there's a swapping of the 1 and the 2. Okay. Now I'm getting nervous because I think... Okay, never mind. 1. 1. So we want to put this number over here, right? Okay, and then we want to say that u increases with a small number times y. No, sorry, u increases... I'm considering y less than epsilon. Okay.
Linear relationship u is y plus 1 over 1 Are you expanding it?
Epsilon is small. That's a large number. So epsilon is small, right? So this is a very large number over here, e to the minus a lot. So this term goes away. So we have a 1 on the bottom. And then on the top, I have e to the minus, right, y over epsilon. Okay? And y over epsilon is my small parameter. So I can expand that, right? And so I'm going to get 1 minus 1, which goes away.
You've already got the y. So you're expanding the first order to the exponent.
So I'm going to expand the top, right? So 1 minus e to the minus y over epsilon. Okay. So this is equal to 1 minus y over epsilon.
So that's what
Okay. So these guys goes away, and I'm left with y over epsilon. Okay. Okay, which is a small thing. So I was right before. No, because y is small compared to epsilon.
But it's still that's a high slope. Slope is 1 minus 1.
Your slope is 1 over epsilon. Yeah, right.
My slope is 1 over epsilon.
1 plus 1 over epsilon.
Yeah, I think I had this right before. Okay, let me just get this right over here. Okay, so my y value is staying small compared to epsilon. Okay, so I can't go up much in this direction over here, right? But u can go all the way to approximately 1, right? Because when y is equal to epsilon, then u is equal to 1. So I put a point over here within epsilon of this origin over here, okay, and I join these two over here. Everybody happy with this? Okay, good. And then over here, I get a turning point. Okay, so now we're going to consider the limit of y much bigger than epsilon. Okay, and so I pick up a slope of 1, and u becomes proportional to y. Okay, so between these 2 points over here, I'm going to come up like this. Everybody happy?
It's a particle accelerating under, with some friction and gravitational force.
Yes.
So
That's more or less what you would expect.
velocity and the,
Exactly.
that's the terminal velocity.
That's the terminal velocity, and that's the, yes, exactly. Okay. Everybody happy? This is supposed to be really easy. This is why I'm doing this. Okay, so this is our plot of this function over here, right? And what we see is that there's kind of two regimes for the system. There's this very small length, okay, where things kind of happen inside this very small length, and then suddenly, or not so suddenly, but sort of smoothly, this kind of length becomes unimportant, and we change the character of the solution. Okay. So what I want to do now is say, well, we've solved this exactly, okay, and we've plotted the solution. Let's now go back and let's kind of put in. Let's look at what would happen if we did the same thing that we did when we took the Reynolds number to be very large, or we took the Reynolds number to be very small. Okay? So our differential equation was epsilon times d2u by dy squared plus du by dy is equal to 1. Right? And what we did before is we basically had a very small parameter, which was the Reynolds number in that case over there, and we chose to neglect this term over here, and then we went ahead and solved. So we can do the same thing over here. Right? And so now what we have is we have du by dy is equal to 1. Okay? And so is that the order I want to do it in? Yes. Okay, good. So then u, right, is equal to y plus some number. Okay? And we know that u at y equals to 1 has got to be equal to 2. Right? So that tells us that this number is equal to 1. So our solution, just by putting that boundary condition, is u is equal to y plus 1. Exactly. So what's the problem with this? Say again? You had it right, so. We don't have a second boundary condition that we're allowed to use. That's precisely the problem. Okay? So we're incapable of enforcing our boundary conditions. Okay? And how did that happen? We reduced the order of the differential equation, exactly. So we did something that seemed innocent, dropping a term, but in fact we changed the whole character of the solutions that we can access. In particular, we killed our ability to put two boundary conditions in, which we have in a real fluids problem, and we had in this case over 2. Okay? So what we did is we came up with an approximation, and we came up with a solution which is in fact a pretty good solution, right? Y plus 1, a slope of 1 and an intercept of 1. This is a pretty good approximation to the exact solution. However, by making this kind of seemingly innocent kind of dropping of this term, we neglected a whole kind of dynamic, right, which makes it impossible for this kind of coarse-grained description to satisfy the boundary conditions. Okay? And so what we can do now is we can say, okay, well, how can I capture that? What would I have to do to capture that? Well, any guesses? Exactly. Right? We expect that everything is going to be fine up until we get very close to this region over here. And we know that y is going to be infinitesimal in this region over here. Okay? But all the physics is in this region over here. So then the natural thing to do is to rescale y so it's not sort of infinitesimal in that region over there. Okay? So we're going to make a transformation. We're going to take a new variable, y, which is equal to the old variable divided by epsilon. So we can plug this back in. So we get epsilon times 1 over epsilon squared. Okay. d2 u by dy squared plus 1 over epsilon du by dx is equal to 1. U by dy is equal to 1. Okay. So we can basically multiply everything by epsilon, right? And the equation which we find is just d2u by dy squared plus du by dy is equal to 0. Okay. And now we can go and solve this equation over here. So this is going to give us that u is equal to a times 1 minus e to the minus y. Okay. Can anybody tell me what boundary condition we should be using? The inner boundary condition. Okay. So the inner boundary condition is that as y approaches 1, we want to match the other solution, right? Which was 1. So that fixes a to be equal to 1. And so now what we've done is we found ourselves two solutions to our problem. We have a problem which is a solution which is 1 minus e to the minus y over epsilon for a region y which is smaller than epsilon. And then we have a solution which is 1 plus y in a region y, I guess it's sort of that order, which is greater than epsilon. Right? And in fact, we can now go back and take our full solution and take these two limits and verify that we get the right thing. Okay? But the key point is that what you've seen is that taking these limits of high Reynolds number and just dropping a term in the equation, or low Reynolds number and dropping a term in the equation, really fundamentally changes not just kind of some details, it changes the whole character of the equation. Okay? And you can recover this character by going back and then thinking more carefully about different parts of the fluid having different characters, and then thinking about gluing these characters together. And we did that in the context of an exactly solvable model, okay, where we had a differential equation, we could solve it exactly, and we could find that it had these two regions. In general, you can't do that. Right? But in general, what you do often and always have in these problems is precisely this sort of separation. You have a region in which you can think about the flow with one character, which is the high Reynolds number flow. For example, you would do this for an airplane if you're thinking about calculating the lift for an airplane and the flow around it. But then you have this little region close to the wing where you have to really you can't just say, oh, it's inertia dominated. If your length scale gets small enough, the Reynolds number is going to get small enough, and you have to go and worry about the other character. And a lot of fluids is about finding the character of the flow in different parts of the flow and matching these together.
So really the problem is that the drop wasn't really small if you go close.
Exactly. In other words, the fluid found the way to make the term that we dropped not really small in the region really close to the edge. Right? And this is a general thing that happens. Yes? As I bring up a video. Yeah, go. For low Reynolds numbers, you don't really have this problem so much. It's if you have if it's for high Reynolds number that you have these problems more often than not. Yes?
Is this related to what Effie was talking about with the tennis ball? So where you're near the boundary layer, you don't realize what the length scale is. Like you get a different length scale if you're close to the boundary.
You get a different length scale because you're close to the boundary. Yes. Yes. Exactly.
Do we need to do asymptotic
At the interfaces between the two is where you're sort of matching.
Yes, we need
Yes.
to asymptotically match them.
Yes, exactly. So there's an entire, what I'm trying to emphasize over here is the basic idea in an example in which you can really see what happens when you drop the second order term in your differential equation. Right? And sort of the origin of why you would expect these two things. And then for the more general problem, some of these you can solve more or less exactly, but let me just show you a video to illustrate how this is general. This is the same kind of setup we had last time, flow going this way, except now occasionally they have been labeling the flow also in this direction, so you get a sense of the speed, not just the streamlines. Then we're going to take a flat plate, and we're going to insert this. This was a high Reynolds number if you look away, and in fact the flow just continues with no distortion. But if you look close to the edge, you find this boundary layer forming over here. And this boundary layer kind of grows as the square root of the size. Everybody happy? Man, we're not getting, I feel like Eric earlier. There's all this great stuff that we're not going to get to do. How about the character of this boundary layer? Okay, so we've seen that in general, right, we're going to get something like this, right, because otherwise we can't enforce our boundary conditions. So we have to have something like this. What's the character of the flow inside this boundary layer? Viscous, yes, that's true. That's the character in sort of broader terms. But if we think a little bit more in terms of what we were doing at the beginning of last time, when we were sort of plotting, we were thinking about, how you think about a flow, and we were decomposing the flow in various terms. What would you think about those three flows? Yes, exactly. So what's going on in this boundary layer is that there's a very high gradient of velocity. So this is our boundary. We have zero velocity over here, but then the velocity rapidly grows. Okay? So we have a big gradient in velocity in this direction over here. Okay? So that means that we have a big dy of Vx. And so what's the consequence of having a big dy Vx in this problem? If we think back at our three ways of thinking about decomposing a gradient in velocity. Hint, there's only two. Remember, we consider the flow like this, where the velocity in the x direction was equal to some number times y. Okay, then we yes, so good. So we had shear and rotations. Right, and that's just because if we think about decomposing the flow, right, then we have 0, alpha, 0, 0, and this is equal to 1/2 the rotational part plus 1/2 the pure shear part. Okay? And it's a very, very high value of this derivative over here. So in fact, in general, in these boundary layers, what you have is a very high degree of vorticity, right? And you have a lot of shear going on. And these two things kind of can play on each other to lead to a big development of the boundary layer into something more complicated, into instabilities. Yes?
So you can think of it as it's a transition in space between what you assumed is a low Reynolds number to a high Reynolds number.
Yes, exactly.
So near the boundary, it's always high Reynolds number. If you
Near the boundary, it's always low Reynolds number.
Viscous dominated.
oh, this
Yes.
is dominant, sorry.
Exactly.
So you can't throw out terms that you would otherwise.
Yes, exactly. Yes. And this is kind of a big part of how you proceed with fluids. You sort of, you make some assumption, you kill some term, you solve, you go back, then you look for self-consistency. And then we found, for example, in this case, that we couldn't enforce a boundary condition, so we knew something was up. And then you try to piece it together. Right? So in general, if you have a complicated flow that looks something like, I don't know, you have a flow coming onto, say, a sphere, for example, and you might have seen some of these flows look something like this, or this could be a flat plate or something. In fact, maybe we could just make this a tree, right? So we could have an obstacle like this, right? And then you'd have different regions of the flow that have different character to them. So this, for example, would be a region with no vorticity, right? And it'd be a region which is far from the boundary. So this is high Reynolds number, no vorticity. This becomes potential flow. Yes. Over here. Yes. So then you can zoom in to this region. First of all, you can zoom into this region over here, and you'll have the type of problem that we talked about so far. You're going to have a boundary layer, and you're going to have to worry about that. And you're going to have to match the flow inside here to the potential flow outside here. Over here, you're still going to be viscous, and you're going to have another type of flow, which is called a corner flow. Okay? And this is going to be low Reynolds number, and you have to worry about that. And then you have to see how that goes as you go away, and you match it onto this potential one. Once you get to this side over here, you start to generate vortices, which is what we're going to talk about. In fact, next time is going to be a combination of seminar and lecture on vortex dynamics. And so now you no longer have potential flow because you have vortices inside the flow. Okay, but you're still at high Reynolds number, and you're away from the boundary, and so on and so forth. And solving a flow like this really involves writing different equations for different parts of the flow and then matching them together. Yep.
So the vortices are generated because of the tree, or is it the boundary layer that is sort of going there and creating the
That's a good question. It can happen in different ways. If you accelerate objects, you can create vortices without it being a boundary layer separation, but you can also generate them by boundary layer separation. So that's important. And let's see. I don't know if we have time for. Well, we might begin our discussion about vortices, but I just want to make one more comment about this business that we did of finding a characteristic parameter that models our flow, right? And seeing that in fact our equations were the same equation, just modeled by this parameter over here, by the Reynolds number in this particular case, and you should therefore get the same solution or the same behavior of your solution, right? If you change the length scale and decrease the velocity, or if you change the viscosity, make it smaller, and you make the length scale correspondingly smaller, or the velocity correspondingly smaller. You can take any combination of u naught, right, L naught, and u, and as long as this is the same number, the equation is the same, the solution should be the same, right? And this has a very powerful consequence in fluids especially, because in most circumstances you can't solve the equations. In many circumstances which are very relevant to everyday life, you can't solve the equations. Right? So if you want to design a building and you want to know if it can withstand large winds, like we have in Chicago, then what do you do? Right? And the answer is what you do, and what you still do to this day, is you take a 3D printer and you print Chicago, right? But you print Chicago on a much smaller scale, okay? So we made L naught kind of much smaller. So then you correspondingly increase U naught, right? And if possible, you do something about nu as well. Okay? And the solution most commonly adopted in these circumstances is to use air and to use a big turbofan kind of fan, basically, to generate a very, very high U0, so that your shrunken Chicago is still kind of at the same Reynolds number that the real Chicago is, which is very, very high, incidentally. And this is something you do not just for architecture. So here's an example. Here's one of those turbofans up there in the back. This is not, okay. I didn't find Chicago, but there you go. This is this building over here, and they want to know what these buildings over here are going to do to this building over here, so that they can make it so it doesn't fall. And this is still to date how you do this. Okay.
How do they
Yeah?
decide, I mean, the length scale from like this building they want?
Yes.
I mean, how do they decide and how do they know we can stop here?
Oh, well, I mean, at some point you worry about steel and stuff. I mean, I don't think I understand the question.
You want to measure a specific building, and what the example showed, so we do some radius around that building. But where would the equation have this characteristic length scale from which you say that maybe the other buildings around them can't do much?
Oh, that's a good question. As far as I know, that's relatively empirical. It's relatively empirical, because you have a flat. You have on one hand you have the lake, on the other hand you have the south side. So for all these different things, there's different kind of airflows coming in, and you sort of have a figure of merit for the shadow from wind. Part of it involves the dissipation. So most of the wakes, which are the difficult things to calculate, correspond to vortices in them. And you can estimate the time of, it's basically turbulence. And you can estimate the time that it takes turbulence to decay from the viscosity. And so that will give you one contribution to your length scales. And then the details, those you kind of... and then you put in a factor of 5. Yes?
Decrease L and you don't change the viscosity.
Yes?
You have pictures of airplanes, and the airplanes are already traveling at speed and stuff.
Yes? Well, you can't you can't necessarily capture all the scaling in these problems over here, but you can still capture some parts of the solution that you don't really know what it's going to do. It's a good question, but you have the you're worried about. Yes, exactly. I mean, for example, when you're flying along really fast, that's one kind of area of aerodynamics. But one of the things that you're really interested if you're designing an airplane is, and in fact, it's interesting for many reasons, but very important reasons, is you want to know what your airplane does when it's going very slowly, right? Because what happens is when you're going very, very slowly, and you're not accelerating downwards, you're generating enough lift to balance your weight, but you're going very slowly. For a wing, that means that you're bringing the angle of the wing to be very high. And there's this kind of magic number, which comes from experiment, which is around 17 degrees, at which point the flow can no longer go smoothly over the wing and separates. Okay? In fact, I might even have a video of that. And that's called a stall. And it's not like a car engine stall, where the engine just stops. It's much worse. You stop flying, and you start falling. And it can be a problem. And in particular, when you're in this stall, you can get yourself into a spin, right? And then in these big airplanes, you're in big, big trouble. So that's a big part of what they care about. And for that, the actual speed would be much lower. And so you can reach that Reynolds number by having the small scale and the big thing. They're not that. They're pretty big scales by that machine. So for the slow flight, you can capture it with this, and the fast flight, you patch together what you can. Okay. So in fact, let me just show you this video. I think I can do this, and oops. Come on. No? Okay, I don't have the video for you today. I will give you a link to the video on the website. The last comment I want to make is just an introduction to the next lecture, which is going to be part seminar, part lecture. Okay, which is we've considered so far the viscous limit, and we've seen a very nice demonstration of the what happens at very low Reynolds numbers. We've looked at a toy model and solved an analytical problem for a relatively higher Reynolds number, and we've seen about what happens in this kind of intermediate region where you have to glue together. Right? But there's, of course, a very interesting regime, which we haven't talked about, which is the regime of just being in high Reynolds number away from boundaries. Okay? And there, the kind of element that plays the biggest role of everything is vorticity. Okay? And you can see this by just considering by very simple considerations. Okay? The vorticity is equal to the curl of the velocity, okay? And the divergence of the velocity is equal to 0. Okay? So if this is equal to 0, the curl of the vector field is equal to 0, and the divergence of the vector field is equal to 0. And what does that give you? It gives you, exactly, it tells you that the velocity is proportional to the gradient of some function, right? Which tells you that since v is equal to the gradient of some function, then the relevant equation is the Laplace equation. And what do we know about the Laplace equation? It sort of came up earlier in Eric's talk. The length scales are dictated by the boundary. They don't have intrinsic length scales. So if you go far away from a boundary, right, and you don't have vorticity, and your fluid is incompressible, you have nothing. You just have no activity in the fluid at all. So if you want to characterize these fluids which are sort of turbulent, or you want to characterize these fluids which have a lot of motion and a lot of dynamics to them away from boundaries, then the degree of freedom that you have to consider is the vorticity. And the simplest demonstration of this fact, okay, it's on, is the following. You can take actually, let me just ask very quickly. No, let me not ask. Let me just do. Okay, so everybody knows what I'm about to do, right? Okay. What I'm about to do is I'm about to demonstrate that by injecting some vorticity into the fluid, I can have an effect very, very far away from the boundaries. Okay. This one works a little bit better. Okay. And the next lecture, I should thank. We have no smoke. Okay. Well, you're gonna have to play with this after class. The next lecture, what we're going to do is we're going to begin by. Whilst we wait. In the next lecture, what we're going to do is we're going to begin by, from this observation, we're going to begin from the observation that the character of flow away from boundaries is kind of captured by the non-zero vorticity. We're going to rewrite the equations in terms of the vorticity. And from that, we're going to go back and we're going to reinterpret some of what we've done. And we're going to introduce a completely new concept that is peculiar to fluid dynamics, which emerges from the vorticity, which is that fluids, in addition to the conserved quantities that we put into them, which were energy, momentum, right, and mass conservation that we use to set them up, have an emergent conserved quantity, which is peculiar to fluids. And this emergent conserved quantity is best understood when you look at fluids in terms of vorticity, and it's called the helicity. And it actually connects to everything that we've been talking about in the first week, which is it connects to topology. The interpretation of this emergent conserved quantity that you have inside fluids, that's based on the vorticity, emerges from, oh, come on. There you go. Okay? How's that for an effect far away from boundaries? Okay? You can play with this afterwards. So we'll connect back to the first week, right? In 1 week's time, we'll take what we learned and we'll connect it back to topology, and we will see what happens. Thank you. And you can come play if you like. Until you set the fire alarm off.